if I have a 3-variable function like that one there, I represent it as such: a, b, c, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay? The thing about Karnaugh Map is boxes that are physically adjacent, they are also Boolean adjacent. What does Boolean adjacent mean? We know what is physical adjacent. Physical adjacent means two boxes that are next to each other, right? Okay, so these are physically adjacent. These are physically adjacent. These are physically adjacent. Well, these are physically adjacent, even though they're on the two sides. But then we can visualize a Karnaugh map as a circular plane that this and this become adjacent also. All right, so if you look at all these adjacent terms, let's look at this one. For this one over here, A is 1, B is 1, C is 0. For the one below that, A is 1, B is 1, C is 1. So the upper box corresponds to A, B, C bar. The lower box corresponds to A, B, C. These two terms are only different in one variable, and that's why we call them adjacent. If I take these two, okay, let me clean this Karnaugh map. If I take A, B, C bar, which is the upper box, or that with A, B, C, which is the lower box, A, B, C or C bar, okay, let's say you have a 1 here, you have a 1 here, A, B, C or C bar is 1, and therefore this reduces to A and to AB, okay. When this reduction is done, I can go back and look at my Karnaugh map and say this: well, why didn't I realize this in the first place? Why couldn't I just, instead of writing this one and calling it ABC bar, and then this one calling it ABC, and then perform these Boolean algebra laws, why couldn't I, from the very beginning, look at these two, okay, look at these two and say, well, these are physically adjacent, and the variable between two physically adjacent boxes drops, and the term corresponding to these physically adjacent boxes is the term that includes all the variables that are shared between all these boxes. Okay, now in the green box I'm showing A is 1, B is 1, no other variable is shared, no other variable is the same between these boxes, and therefore that green box can be directly written as A ended with B. Okay, that's the whole thing about Karnaugh maps. Okay, let me, before getting into my larger example here, let me go back and redo this. Well, I'll redo that once I get into the concepts of Karnaugh map. Alright, so let's continue with what I'm showing over here. Let's say I have a function a bar b c, a b bar c, a b c, a b c bar. Okay, I have three variables, and the truth table corresponding to this is it has a 1 in position 0, 1, 1, 0, 1, 1. It has a 1 in position 1, 0, 1, 1, 1, 1, and 1, 1, 0. Okay, so it has ones in these four positions. Actually, I could write this function as sum of minterms. This is number 3, this is number 5, this is number 7, and this is number 6. Okay, that means it has ones in row number 3, 5, 6, and 7. 3, 5, 6, and 7. Actually, I call these terms the minterms of my function. A minterm is a product term that includes all the variables of a function. Okay, and therefore here I have 1, 2, 3, 4 mean terms, and these mean terms are these here. Okay, these are all terminology. I'm representing this function by list of its mean terms. This. Actually, this is no different than this, and no different than this. All three forms are representing my function in terms of my function's mean terms. Okay? Now, instead of showing my truth table, this is called the truth table. Instead of showing my function using a truth table, I use a two-dimensional table. Something like this. Okay? A two-dimensional table where A, B, and C are the variables of the table, and where I will be very careful in positioning the entries in the table such that two physically adjacent boxes will become will have Boolean correspondence that are also Boolean adjacent. Okay, and therefore the box, the Karnaugh map I draw becomes like 0, 0, 0, 1. If I put 1, 1 here, then this box, okay, I'm sorry, if I put 1, 0 here, this box has A0, B0, C1. The lower box has A0, B1, C0. That means two variables are different, and therefore I'm not going to put 1, 0 here. I'm going to put 1, 1 here. Therefore, corresponding term to this is A0, B0, C. Corresponding expression to this is A0, B, C. And therefore, there is only one difference between these two boxes, and therefore the whole thing about Karnaugh map is exactly this. Two physically adjacent boxes have product terms that correspond to them that are also Boolean adjacent. All right, so I start with this Karnaugh map here, and this is 0, 0, 0. That means box number 0, box number 2, box number 1, box number 2, 3, 4, 5, 6, 7. And let's put a 1 in position 3, 5, 6, and 7. A 1 in position 3, 5, 6, and 7. So this is the Karnaugh map. Okay? Now, in order to be able to reduce this, I'm going to look at these two terms. Okay? They share BC. These two, they share AB. These two, they share AC. And therefore, the resulting Boolean expression for this expression is exactly what I'm showing over here. AB, BC, and AC. All right. Let's cover some terminologies. Boolean adjacency. Two product terms are Boolean adjacent. Okay. Two product terms are Boolean adjacent. A, B, C. A, B bar, C. Okay. If they consist of the same Boolean variables like ABC, ABC, and only one variable appears in its true form in one and in complementary form in another. Okay, like that. Only one variable, that means B, B bar, true form in one, complementary form in another. Physical adjacency, if you have two boxes that are either horizontally next to each other or vertically next to each other, like these two, or like these two, these are called Boolean adjacent. Karnaugh Map tries to make sure that whatever is physically adjacent is also Boolean adjacent. This is a Karnaugh Map. Let's draw it here. This is a Karnaugh Map with 3 variables. These 2 boxes, okay, it's a 1, 0, 1, that means A, B bar, C for this, A, B, C for this, and therefore these 2 can be turned into A, C. This one, the upper one is A bar, B bar, C bar. The lower one is A bar, B, C. Okay, there are 2 product terms. That means these are all ANDed together. And then there is a sorry, this 1, 0. Okay, and they are only different in B. That means the term here is A bar, C bar, that these 2 product terms reduce to. That means these are Boolean adjacent. Well, if you want to look at the physical adjacency, they are not directly horizontally or vertically next to each other. But then if you look at it this way, if you look at this as a circular plane, then you will see that yes, indeed, the upper box and the lower box are adjacent, and therefore you have A bar, C bar. Okay? The whole thing about Karnaugh Maps is Boolean adjacency and physical adjacency are correspond to this to each other. Okay, if you look at the 4 variable map, this is how you draw your variables. Okay, and again, you on the columns you put 0, 0, 0, 1, 1, 1, 1, 0. On the rows you put 0, 0, 0, 1, 1, 1, 1, 0. This is the same example I was showing that reduces to these 3 terms over here. Okay, and more examples. Let's look at this. Okay, let's look at this expression here: A bar B C, A B bar C, A B C, A B C bar. Okay, that's the same thing. This is min term number 3, min term number 5, min term number 7, and min term number 6. How would I do this if I did not have Karnaugh Maps? Well, if I did not have Karnaugh Maps, this is how I would do it. I would take, let's say, okay. Yeah, I would bring ABC here. Okay. AB bar C here. I would repeat ABC twice. Okay. ABC bar I would keep here. I would repeat ABC one more time. Okay. So here ABC is repeated 3 times. Once it's put next to ABC bar, once it's put next to AB bar C, once it's put next to A bar B C. Okay, let's combine these two because they are adjacent terms, and therefore I take A bar or A, and this becomes, actually I take B C, factor it out, this becomes A bar or A. Okay, so this becomes this one over here. And then I'm going to take these two, factor out AC, and this becomes this one over here. Okay. Third one, I'm going to factor out AB, and this becomes this one over here. Okay. Let me show that to you on a Karnaugh map. I've shown that already, but I'm showing the Boolean equivalent of it. The original function 3, 5, 6, and 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay, these are the places where I put a 1. These are places that correspond to these min terms I'm showing over here. Okay, what I did was the green one, A bar B C. Let's show that in green. Okay. Then I circled these two boxes. This is AC. And then I circled these two boxes. I have circled two min terms at a time, but then this min term right in the middle is being mapped by all these maps that I'm creating. Actually, mapping this one by the three colors means that I have used that term 3 times. A, B, C has been used 3 times. Okay, which is okay, because in Boolean algebra I say that A or A is A. Actually, A or A or A is A, and therefore the term ABC, I needed it for 3 times here. I could use it 10 times if I needed it that many. And therefore, that has been able, let's go back to the Boolean algebra. This has been able to turn the green form, okay, to be NC, and A or A bar, well, that's a 1. 1 drops, and therefore that turns into BC. The dark blue form turns into AC, and then this is the dark blue. And then the brown one turns into this. So that's what I'm saying. What I'm saying is, instead of going through these Boolean algebra steps, if I can just look at this and find out that indeed the green map has only variables B and C, I would be able to write this directly as such. I look at the dark blue and find that the variables that are common between these, A is 1 in all boxes, C is 1 in all boxes, and therefore this is A and C. Finally, the variables that are the same in all these boxes, A is 1 in all the 2 boxes, and B is 1 in all these 2 boxes, and therefore this is A and B. Alright, so I can have 4 variable maps, and the same thing applies, except that in 4 variable maps you can have 2 maps that are also adjacent. Okay, before getting into the example here, let's look at this situation. Here's a 4 variable map, A, B, C, D. 1, 1, 1, 1. Okay? These two are A, C bar, D. The one below is A, C, D. Okay? Now look at these two terms. These two themselves are adjacent, meaning that ACD or AC bar D, you can factor AD, and then this becomes C or C bar, this becomes 1, and this becomes D. Okay, AD. Okay, then I say, well, instead of writing all these steps, why couldn't I, just from the very beginning, circle all these 4 boxes and then look for variables that do not change between these 4 boxes. Okay, the variables are A is 1 in all these 4, D is 1 in all these 4, so I could just take this and write AD directly. Okay, let's look at the example I have here. Let's say I have a truth table. There is a, this is position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Karnaugh map is numbered as such. A, B, C, D. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, here I have a 1 on 0, I have a 1 on 2, I have a 1 on 8, on 10, on 11, and on 15. Okay, so a 1 on 0, this one, a 1 on 2, this one, nothing on 3, 4, 5, 6, 7, there is a 1 on 8, 9, there is a 1 on 10, there is a 1 on 11, and finally there is a 1 on 15. Okay, now I want to minimize this. These two ones are adjacent. Let's find the I'm gonna erase these now that we have the correspondence. These two ones have in both places, A is 1, B is 1 in 1, in 0 is 1, so that drops. C is 1, D is 1, and therefore this is one of the product terms of my result. And then I have 2 boxes over on the 2 sides up and 2 boxes on the 2 sides down. If I look at these, I find that this one is 0, 0, 1, 0. Okay, this one is 1, 0, 1, 0. There is only one difference between these two. The upper one, 0, 0, 0, 0. 1, 0, 0, 0. There is only one difference between these two, and therefore this one drops to reduces. The upper one reduces to B bar, C bar, D bar. The lower one reduced to, again, A is dropped, B bar, C, D. Now let's look at these two terms. These two terms, they have only B in common and D in common, and therefore I can take these 4 together and then say, well, let's look at all the variables that are the same in all four boxes, I find that b is the same. See, b is 0 in all four boxes, and then d is the same in all four boxes, so this becomes b bar d bar. What did I just do? Well, what I did was, remember before I said that you can take a Karnaugh map and look at the three variable Karnaugh map. You look at these two ones here and here, and then you say that this is like a circle, and the ones I'm marking over here, they are adjacent. Okay, I'm going to take this further and say, well, I'm going to look at my four variable Karnaugh map as a spherical plane, meaning that this and this, this and this, if you go back to the back of the Karnaugh map, you see these four being adjacent ones, and therefore you can map them all together and look for common variables between them that turn out to be b and d only, and b bar or d bar only, and therefore this becomes b bar d bar. If you are to build this, well, I can either build it using AND gates and OR gates, or I can build it using NAND gates. To build this using NAND gates, this is what I do. Double bar it, okay, and then this becomes, take the upper bar, break the lower bar, A, C, D, B bar, D bar, oops, okay. What it means is an AND gate ACD, an AND gate B bar D bar, and then the results are NANDed together. Okay, I'm going to show you another way of doing the same thing. We could start with ACD, A, C, D, B bar, D bar, okay, and OR them together. Okay, I can take a line and put two bubbles on the two ends of it. I can take a line and put two bubbles on the two ends of it. So this is an AND, this is an AND. What is this? Well, what that is this is, let's say IJ, I bar, ORed with J bar, which is, let's double bar it, I bar, ORed with J bar, right? Which is, take the upper bar, break the lower bar, becomes I and J, and therefore this is no different than an AND gate. Okay, and therefore here I have three NAND gates building my circuit. So this circuit and this circuit, or this way of representing the circuits, is the same. Whether you show a NAND gate here or an OR gate with inverted inputs. What has happened for the four corners is this. A bar, B bar, C bar, D bar is northwest. Okay, I'm going to redraw this. 0, 0, 0, 1, 1, 1, 1, 0. A bar, B bar, I'm sorry, this one is A, B bar, C bar, D. Okay, this is the northeast. Okay, then I have A bar, B bar, C, D bar. This is the southwest, and this one is the southeast. Okay, I'm gonna take these two, the upper two, and factor out B bar, C bar, D bar. I come up with A bar or A. Okay, Alright, let's factor the common terms b bar, c bar, d bar from the northwest term and the northeast term, or the two north terms, and then that becomes b bar, c bar, d bar, ended with a bar or a, which reduces to b bar, c bar, d bar. Then I have a bar, b bar, c, d bar, or the southern terms, and then find common things between them. You find b bar, c, d bar, and then factor out a or a bar. That becomes b bar, c, d bar, and this one is b bar, c bar, d bar. And then now let's factor out the common terms between those, which is b bar, d bar, c or c bar, and then becomes b bar, d bar. What it means is exactly what we said before. Instead of having to write these four, you can visualize them as being adjacent, and then just write one term that corresponds to the variables that they all four boxes have the same, and or variables that are the same in all four boxes, and therefore b bar, d bar.